Hi everyone, this is Maverick Paul, the chemistry guru. Now in this video, we want to calculate the mass of black powder required to fire a cannonball. So let's take a look at this question. In the middle of the 15th century, black powder was widely used by the Arabs as propellant for muzzle loading cannons. So black powder consists of a mixture of potassium nitrate, sulfur and charcoal, which is carbon, in the molar ratio as shown in the equation below. So we have 2 KNO3 plus sulfur plus 3 carbon. All of them, they are in a solid state to give me K2S solid plus N2 gas and 3 carbon dioxide gas. So the question says that given that 2.00 mole of gas could just expel the cannonball out of the cannon tube, what is the minimum mass of black powder in grams required for this to happen? And we are given 4 options A, B, C, D. So we want to calculate the mass of black powder required to produce 2.00 mole of gas. Of course, the topic tested in this question is on mole concept. So what we have to do is we have to look at the mole ratio between the reactant and the product. And from there, we compare mole ratio to try to figure out the number of moles of reactants required and subsequently determine the mass of the reactants required. So let's take a look at the balance equation. Now given the balance equation in the question, I have 2 moles of KNO3, 1 mole of sulfur, 3 moles of carbon. So altogether we will have 6 moles of reactants. All of them, they are in the solid state, and involving the products, we are only interested in the gaseous product. So I have 1 mole of N2 gas and 3 moles of carbon dioxide gas, 4 moles of gaseous product. So effectively what we have is, in terms of the mole ratio, the number of mole of reactants to the number of mole of gas is 6 moles of reactants to 4 mole of gas. The mole ratio is here, 6:4. Of course, we can simplify this to 3:2. So given that we have 2.00 mole of gaseous products that is being formed, then we can calculate the number of moles of reactants, which will be 3/2 multiplied by number of mole of gas. Then I can substitute the number of mole of gas to be 2.00 into this equation. I can solve for moles for reactant is 3.00 moles. Now take note, this number of moles of reactants, which is 3.00 mole, will be the total number of moles of your KNO3, your sulfur, and your carbon. So what we have to do next is we have to split these 3 moles up. How many moles of your KNO3 is required, and how many moles of sulfur is required, and how many moles of carbon is required. So what we are going to do next is this. I have to consider, in total I have 3.00 moles of reactants, and I want to split them up. How many moles of each of these solids are involved to give me in total 3 moles of your reactant. And you notice altogether we have 6 moles of the reactants. So given this mixture, I have 2 moles of KNO3. So the number of mole of KNO3 will be 2 parts divided by a total of 6 parts, multiplied by 3.00 mole of your reactant. I'll get 1.00 mole of KNO3. So basically, out of 3 moles of reactants, 1.00 mole of this reactant will belong to KNO3. Now we can do the same for sulfur and carbon. I know that out of a total of 6 parts, 1 part is sulfur. So the number of mole of sulfur will be 1 divided by 6 multiplied by 3, which is 0.500 mole. And involving my carbon, out of 6 parts, I have 3 parts carbon. So the number of mole of your carbon will be 3 divided by 6 multiplied by 3.00 mole, which is 1.50 mole. So effectively what we have done is we have split this 3.00 mole of reactant to 1.00 mole of KNO3, 0.500 mole of sulfur, and 1.50 mole of carbon. Now the next thing we want to do is we want to determine the mass involved. So 1.00 mole of KNO3, I can multiply this by the molar mass for potassium nitrate. So 39.1 is the atomic mass for potassium, 14.0 is the atomic mass for nitrogen, 16.0 is the atomic mass for oxygen. And we have 3 of them, so we have to times 3 here. So we can work this out. The mass of KNO3 involved will be 101.1 gram. Now, again, we can do the same for sulfur and carbon. Mass of sulfur involved will be number of moles, 0.5, multiplied by the atomic mass for sulfur, 32.1. So I'll get 16.05 gram. Mass of carbon will be number of mole of carbon, 1.50, multiplied by atomic mass of carbon, 12.0, which will give me 18 grams. So these are all the masses for your potassium nitrate, for your sulfur and your carbon. I just need to simply add everything together to get the total mass of black powder. So total mass will be 101.1 gram for KNO3, 16.05 gram for sulfur, 18 gram for carbon. We add everything up, total mass will be 135.2 grams. So what we can do now is we can look back at the options A, B, C, D. The closest answer that we have should be B, 136 grams. Now, there's actually an alternative way for us to interpret the mole ratio. I think it is interesting for us to consider that as well. So let us take a look at this. Now, alternatively, what we can do is, the question mentioned that black powder consists of a mixture of potassium nitrate, sulfur, and carbon in this molar ratio. So what we can do is we can treat this unit 2 moles of KNO3 plus 1 mole of sulfur plus 3 moles of carbon. We treat it as 1 unit and we treat it as 1 mole of black powder. So now the mole ratio is different from what we have done previously. What we do is we just treat this whole bundle as 1 mole of black powder. So 1 mole of black powder will give me 4 moles of gaseous product. The products will still be the same. It will be nitrogen and 3 moles of CO2, correct? So what we can do next is, again, compare mole ratio. 1 mole of black powder, again, the whole bundle is just 1 mole of black powder. The number of mole of black powder to the number of mole of gas is equals to 1:4 based on this mole ratio that we have here. Then I can calculate the number of mole of black powder, which is 1 divided by 4, multiplied by 2 moles of gas. This will give me 0.500 moles. Now, the next thing we have to do is we have to calculate the molar mass of my black powder. Even though this is a mixture, the question did mention that this mixture is in a very specific mole ratio. In a mixture of black powder, we actually have 2 units of KNO3, 1 unit of sulfur and 3 units of carbon in terms of mole ratio. Agree? So this will mean that I can actually calculate the molar mass of this black powder, which consists of, again, 2 units of KNO3, 1 unit of sulfur, 3 units of carbon in terms of moles. I can calculate this molar mass of black powder. So this will be 2 times the molar mass of KNO3, which we have calculated previously, plus 1 unit of sulfur. So this is the atomic mass for sulfur, 32.1. Then this is the atomic mass of carbon multiplied by 3. So the molar mass for black powder will work out to be 270.3. So once we have this, I have the molar mass for black powder, I have the number of mole of black powder required, which is 0.500 mole. Then I can simply find the mass of black powder required, which is the number of moles multiplied by the molar mass, 0.5 multiplied by 270.3. Actually, I will get back the same value, 135.2 gram. Of course, again, if we look back at the options A, B, C, D, the closest answer will still be B, because we are effectively calculating the same mass of black powder. So for this exercise, the answer to this question will be B, 136. Alright, so that was the discussion involving this question, calculating the mass of black powder required for me to expel out a cannonball. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.